All right. Hi, everybody. My name is Ishan, and for the second half of today's lecture, we're going to be looking at a class of models called deep generative models. So in this class, so far, until this point, for the most part, we've been looking at classes of models that use neural networks to interpret data. Most recently images, and then before that sequences, for example, of text, but really any sort of arbitrary, complicated, high-dimensional data. And we've been looking at how we can use neural networks to take that data as input specifically, and then perform some kind of complicated sequential computation on it. But then the output has been more or less something reasonably simple. It's been a probability distribution over classes for the most part. Labels, whether a digit is 0, 1, 2, 3, up through 9. But now I want to take a look at sort of the inverse problem, which is how can we get neural networks to output things that are really complicated? How can we get them to run backwards, so to speak, and generate images in this case, but really all sorts of things, rather than just being able to look at images and interpret them? So this is the target that we're going to build towards. This is a state-of-the-art generative model that's able to generate a wide diversity of pictures within each class, and then a wide variety of classes from the ImageNet data set, which Lex talked to you about previously today. And as you can see, the generations end up being quite varied, and they're also quite true to the form of what they're supposed to be. So these are pictures of, I think, birds, ants, monasteries, and volcanoes. The volcanoes look pretty. The other ones, well, it's trying. So we can generate images. We can also use generative models to generate speech. This is the classic problem of speech synthesis and of getting computers to talk. And recently, what's cool is that, like in a lot of other fields, deep neural networks have gotten to the point where we can just feed them a really large data set of, in fact, raw audio waveforms without doing any sort of pre-processing on them. And a sufficiently big generative model will learn the statistical properties of these waveforms and be able to generate audio that sounds just like it, that's actually convincingly human sounding. So speech synthesis is another important application for generative modeling. Besides that, we can generate things like handwriting. We can feed in a sequence of pen strokes, have a neural network learn what those pen strokes look like, and then ask it to produce more similar-looking pen strokes, and we can get neural networks to handwrite convincingly that way. And the final interesting modality that we might want to talk about is language. If we think about sequences of text as our complicated input that we want to actually output, then we can train neural networks to generate sequences of text, just again by giving them lots of text to look at. And we can use this to do things like what are called conversational agents or dialogue agents. That's what this is an example of. Where you'll have a human say something, like give a sequence of text, and then you'll ask the machine to produce whatever a reasonable response to that sequence of text might be. And you train this model on a big corpus of, I think in this case it is tech support chat logs. And as you can see, the machine actually ends up doing a reasonably good job of emulating a tech support agent. Besides conversation, machine translation is another important application of generative modeling of text. So you can think of the problem of translating a sentence from, say, English to French as the problem of generating a French sentence conditioned on its English translation. So you have machine translation, you have dialogue, and these are important examples of why being able to generate text with neural networks is an exciting application of generative models. So generating things is cool. And there are a lot of really interesting applications in the short term for generative models. But There's something slightly more fundamental that we're trying to get at here, actually, when we do research on generative models. And that is the idea that through learning to generate something, you learn to understand the properties of the data that you're generating. And what I mean by this is, say you are tasked with generating pictures of bedrooms. In order to do a convincing job of generating a picture of a bedroom without simply memorizing your training set, your model has to have internalized a notion of what a bedroom is. And in doing so, its picture of what a bedroom is has to be complete. In the sense that every characteristic that pictures of bedrooms have, your model has to learn. Because if it forgets to learn even one, then the generations that come out the other end will look like unconvincing bedrooms in that respect. Now, again, I'm being a little bit vague about what specifically it means to understand. So I'll try to give some examples here to better illustrate this concept. One important downstream application of generative models is that they're able to assist in classification. So we can take the classification problem that we've been looking at pretty much up till now in this course, and we can ask, how can we make this better through the use of a generative model? How can a sort of understanding of the data help us to better build classifiers for it? So this is a picture of two data points in some hypothetical space. And we train a classifier on these two data points to label the black one as black and the white one as white, say. And our classifier draws a decision boundary in what looks like a pretty sensible place. But we can actually do a lot better than this if we know something about the shape of the distribution that this data comes from. And that's what this right picture is. As soon as we know a little bit about the distribution of data, we can leverage that even if these other data points that we're given don't have class labels associated with them. We now have a much better intuition as to where we want to draw our decision boundary. And we can train a classifier like this that's much more likely to generalize better to new data because it knows sort of what the shape or the manifold of the data that it's looking at looks like. This comes up a lot, actually, in speech recognition, where the way that computers do speech recognition right now is very heavily biased towards looking at the acoustic properties of data. We've built neural networks that are very, very good at reading audio waveforms or spectrograms or other audio features and outputting some kind of transcription. But the way that humans do speech recognition actually relies a lot less on being very, very good at discriminating between subtle features in the audio that we hear and very, very good at being able to infer what people might have said based on what kinds of things are plausible in context. That is, in our heads, we have sort of a generative model of what valid sentences might look like given a certain conversation. And we are in the background applying that generative model as a sort of prior on what the reasonable outputs for the internal speech recognizers in our heads are. For instance, in this conversation I'm having about speech recognition with you guys, if I were to say that it is a very challenging task, in fact, to recognize speech, you would be forgiven for interpreting what I just said as it is a very challenging task to recognize speech. In fact, I said wreck a nice beach, which is entirely a different sentence. So classification is an important application of generative models. Another one is representation learning. We've talked about representation learning in the context of supervised models already, where we've seen that if you train a classifier on ImageNet, for example, and then you chop off the last few layers, then the intermediate representations that this neural network learns actually capture a lot of the details that are semantically relevant to us about the data. They learn to separate dogs and cats well, or at lower level, they learn to separate certain blobs of colors and different types of edges and textures well. Well, it turns out that we can use generative models to do sort of the same trick, but without any ground truth labels. We can do this entirely in an unsupervised setting where we don't have the labels saying this is a cat, this is a dog. All we have is a big data set of images. And this is important because there are a lot of data sets in the world for which collecting those labels is very expensive or, in some cases, even impossible because we don't know what they're going to be beforehand. So being able to learn good representations entirely from unlabeled data is a very important task, and generative models are one way of getting about that. So on the right, this is representations learned on the MNIST dataset by a reasonably state-of-the-art generative model, which we'll look into a little bit later. But you can see that our generative model basically learns a mapping of each point of this. Each point here is one picture of a handwritten digit. And it learns a mapping of those digits into this low-dimensional space. But it's a space where each different kind of digit is very neatly clustered into its own region. The points are colored by what kind of digits they are. So it's the zeros, and then the ones, and then the twos, and so on. The images on the right are another type of generative model learning a representation in which it's learned to separate out a lot of the sort of factors that we consider semantically relevant about this data set. You can see the first picture, it's learned to represent the idea that some of these digits are tilted to the left, and then some of them are tilted to the right. And it's learned to factor that out of the variation in the data. It's also learned stroke width as a concept. That's the bottom image. We can see that it's learned to map its images from very, very thin strokes on the left to thicker strokes on the right. And then finally, of course, it learns digit identity as well. And the final thing that I want to talk about in terms of getting generative models to understand data is that generative models, when trained correctly, can be useful in service of simulation, planning, and things like counterfactual reasoning. And eventually, we want to use this to build intelligent agents and solve machine intelligence in the general sense. If you think about an agent operating in an environment, right, of which you or I are good examples, one necessary component of this is that we all have sort of models of our environment in our heads. We know what our world looks like and how it will respond. We can predict several steps into the future. I know what people's response will be if I say certain things, or if I let go of a pen, the pen will drop to the floor. I can ask myself questions about hypothetical future scenarios, like if I weren't to drop the pen on the floor, and if instead I were to throw it in the air, when would it fall then? And all of this can actually be formalized in terms of building a generative model of your world, conditioned on sort of the actions that you perform on it. And then once we have this generative model, we can sample from future possibilities, or we can evaluate what the likelihood of this generative model generating a certain specific future is. So the graphic on screen is a group of researchers who applied this idea to predicting future frames of the Pac-Man video game, conditioned on what buttons were pressed on the controller. And they built a predictive model that's able to learn what the future several steps ahead looks like. And they're able to use this in service of being able to simulate and plan in the game. And if we think about the game as a sort of microcosm of the world in which we all operate, then this is the relevance of generative models to building sort of artificially intelligent systems down the road. All right, so that's a lot of motivation. Let's talk for just a little bit about formalisms. So far up until this point, the picture of neural networks that we've had is as function approximators. We have a training set, and this training set basically has x-y pairs, x belonging to some space and y belonging to some other space of outputs. And we try to learn a function that maps from the x's to the y's, hopefully in a way that generalizes well. The picture that we're going to talk about for generative modeling is slightly different. Now we still have a training set, but we only have the x's. So we have a training set of examples, x, and we're going to make an assumption. The assumption we make is that the training set was uniformly sampled from some underlying probability distribution. We'll call it P. And the goal of generative modeling, sort of the task that we're trying to achieve, is to recover an approximation that is as close as we can make it to the underlying distribution that generated, or the underlying process that generated our training set. And we want to recover an approximation to it that's as close as we can. Now, this implies that we need a metric for measuring how close our model is to this underlying distribution, just given a bunch of samples from the true distribution. We need a cost function. We need an objective. And the function we use is called max likelihood. And it is specifically that we're trying to maximize the joint likelihood of sampling every single thing from our training set from this generative model that we build. And this translates to maximizing the product of the probabilities of every item in the training set under our model. For reasons of computational convenience, most of the time we do this optimization in the log domain. So actually, we maximize a sum over the training set of log probabilities rather than a product of probabilities. But it comes out to more or less the same thing. And then at generation time, when we want to draw pictures of volcanoes or generate speech or whatever you will, it's as simple as taking our model, our approximation to this probability distribution, and then drawing samples from it. So we can think of generation as sampling from a distribution. We can think of learning as trying to fit a distribution. And we can think of evaluating likelihoods or probabilities under this distribution as estimating how realistic a certain data point is. So this is a picture of what this kind of looks like for a very simple data set and a very simple class of models. This tries to fit a mixture of a few different Gaussians to a data set of points. You can see the points are there, they're the little dots, and you fit the contour lines, which are the generative model that you end up learning to this, and it does a reasonably good job of capturing sort of the shape of this distribution of data. And it manages to pull out a few interesting factors, which is it learns that the data is clustered around these 4 main regions, and that each region has a variance in both dimensions. And that's about the extent that this generative model learns. But you can see it's captured basically a probability density function over this space. And if you were to sample from this density function, you would get a series of points that look not entirely unlike the series of points that it was trained on. So that works when you're trying to fit a very simple sort of model, like in that case, a mixture of Gaussians. But for purposes of this lecture, we're interested, of course, in using neural networks as our density functions, which enable us to sort of model much more complicated distribution shapes over much higher dimensional spaces in a way that generalizes well, if we can do it. So the first naive attempt might be, let's just try to learn this density function directly. Let's train a neural network where you input a certain data point x, and it outputs the likelihood of that value, or the log likelihood, or whatever we want. The problem that we quickly run into is if we train this with the max likelihood objective that we talked about earlier, then that's equivalent to taking each item in the training set, passing it through this neural network, and telling it to push the probability up to 1 of that point. And so you'll get a network that just assigns maximum probability to every point in the space, which in fact makes it an improper probability distribution. Because the characteristic of probability distributions is that if you sum or integrate over the entire space of inputs, the total probability over that space has to be equal to 1. And you're pushing up certain points with this max likelihood cost function, but there's nothing to enforce that everywhere else that you're not explicitly pushing up gets pushed down. The way that you typically would do this is you constrain your model. And the way you do that is you normalize every value by that integral so that the total integral over the space ends up being exactly 1. You make your output some kind of ratio where that integral ends up being in the denominator of the ratio. And so the integral ends up being 1. But the problem is that for complicated neural networks, this integral ends up being intractable. There's no closed form solution to it for most neural networks. And when your space is really big, like the space of like 64 by 64 pixel images or what have you, you can't efficiently approximate it by sampling either. And so this ends up becoming a problem to formulating the problem this way. One solution that people have come up with are a class of models called autoregressive models. Autoregressive models tackle this problem of the normalizing constant in your probability distribution being intractable by factorizing your distribution. So you take a complicated distribution over a large space, P of x, and you factorize it dimension-wise into first a distribution just over the first dimension, and then a distribution over the second dimension conditional on the first, and then the third conditional on the first two, and so on for all of the dimensions in your data set. And what's cool about this is now every individual dimension is a small enough space that our normalizing constant becomes tractable. Either we can calculate it explicitly by summing over the whole space, or we can model that one dimension with a simple enough family of distributions that there's just a closed form solution to it. And we can define valid probability distributions over each of these individual dimensions without having to do the whole thing at once. So there's the way we do this is we build one model. We'll call it a next step prediction model because in a lot of the data we care about, the dimensions are organized neatly into steps. So we build a model to predict the nth dimension or the nth time step or the nth pixel or whatever it is, because our dimensions tend to be ordered into this nice spatial or temporal structure. So we predict the nth step conditioned on all of the previous steps. And we can implement this as an RNN or as a convnet or as any of the sort of neural architectures that you've learned already today. If we're talking about a discrete space where your dimension can take on a set of values like words or characters, then you typically use a softmax output on your network, and you just assign a probability explicitly to every option. If you're talking about a continuous space like images, typically what you'll do is you'll have your network output the parameters to a simple probability distribution, like a Gaussian curve. In this case, your network will output a mu and a sigma. And we'll have these two parameters define the distribution. Or the second thing you can do in the case that you have continuous data is you can just quantize your data into a bunch of buckets, and now you're back in the discrete case where you can just use a softmax. And this actually works surprisingly well. We'll get into it a little later. At generation time, the way you sample from an autoregressive model is you sample the first dimension, and then treating whatever you sampled as the ground truth, you sample the second dimension, and then you sample the third, and you go on in a chain until you end up stopping, basically. So this is what this looks like. You've actually already seen this slide before. This is the RNN language model that we talked about yesterday. But now you get to see it in the context of generative modeling, because in fact an RNN language model is very much a generative model. At each step, it outputs a probability distribution over words or characters or some other kind of token conditional on everything that it's seen before. And you can generate from this by predicting a first word and then sampling from that softmax, and then feeding that back into the network and having it predict the next word, and so on and so forth. But of course, this trick doesn't have to be limited to generating language. We can also use it to generate images. This is some work that's fairly recent called Pixel RNN, where they apply the same idea in 2 dimensions, and they define an RNN language model, basically, that is autoregressive instead of over words in a sentence, over pixel values in an image. And the 2 tricks that they use to make this work effectively are, first, they came up with an efficient formulation where they can train without. They can train this thing efficiently by use of a series of convolutions that are constructed in a special way. And then the second thing that they did is they chose to model each individual pixel not as a continuous value, but as I mentioned, just to quantize it into 256 possible values, an 8-bit integer, basically. And then at each pixel and each color channel, they just use a 256-way softmax layer to predict the distribution over what that color channel is. And that lets them, in theory, approximate any sort of arbitrarily complicated density function over this space. And you can see the generations don't really look globally coherent, but they do a really good job of capturing the sort of finer structure in data. They capture color and texture and those kinds of patterns really well. So autoregressive models are powerful density estimators, to be sure, but they have some problems. The first problem is, I mentioned, you have to generate in a sequence, 1 dimension at a time. And when you do this, it can be really slow. If we think about speech, for instance, audio waveforms exist as a sequence of pressure samples, basically, samples of the pressure wave. And there are about 16,000 of these samples in 1 second of speech quality audio, which means that if you want to generate even a very short sentence of speech, you're talking about generating hundreds of thousands of samples sequentially, which means hundreds of thousands of forward passes of a neural network, which is way too slow to do in real time. The second thing that is troubling about autoregressive models is that we want our networks, in a sense, to reflect as closely as possible structurally the process that we think generated the data. By this, I mean we don't want to generate a picture of a dog by deciding on the value for the top left pixel and then deciding on the value for the next pixel and then the next pixel. We ideally want to think about our models as deciding on some high-level characteristics first. For instance, is the dog standing up or sitting down? What kind of a dog is it? Is it outdoors or indoors? What is its pose? Is it smiling? And having decided on all of these high-level features, we want to sort of generate top-down from that rather than sequentially in a chain. And because autoregressive models constrain us to model architectures which are sort of unnatural in this sense, they tend to focus too heavily on aspects of the data that we don't care about. Think again back to the Pixel RNN picture, where it does a really good job of modeling textures, but there's no real global coherence to the images that get generated. And then the final thing is we've talked about the importance of representation learning and generative models' applicability to that problem. But autoregressive models don't really have a very good sort of internal representation that you can pull out. If you take the hidden layer activations of one of these models, they don't really have any clear interpretability. So I want you to keep this picture in your head of density estimation and of decomposing a distribution autoregressively. But I also want you to put it to the side for a little bit, because I want to talk about a different class of model that is not strictly a generative model, called an autoencoder. An autoencoder is a really beautifully simple model, actually, for doing representation learning. The idea, when we've talked about representation learning in the past, is that you have some kind of classifier, say on ImageNet, where at the bottom you pass in an image and you transform that image sequentially through a series of hidden layers. And then at the top you have a softmax and you have a loss function, and you train this whole thing, forward pass, backward pass. And then you can take the activations from a certain hidden layer and you find out that they are useful for a wide variety of tasks beyond what the classifier was originally trained from. Now, we're interested in doing exactly the same thing, but we're operating in the unsupervised setting where we don't have access to any sort of class labels, so we can't just put a classifier loss function on top. So what we do instead with an autoencoder is we train it to do something very simple, which on its surface might actually seem a little silly, which is we train it to output exactly the same thing that we input. We train it to reconstruct its inputs. We put some inputs in, we pass them through a series of layers, and then the size of our output layer is exactly the size of our input layer, and the cost function we use is just sort of mean squared error between the inputs and the outputs. And this forces the network to learn an identity function of sorts, where it just takes the inputs and it passes them through all these layers and spits them out the other end. And we'll take a certain hidden layer of this network, and we'll call it our latent representation. These are the vectors that come out of this end are the features that we're interested in learning. What autoencoders add to this picture is they take one of the layers and they make it very small, on the order of maybe a few dozen hidden units, much smaller than the space of the entire, than the original space of inputs. And what this means is that in order to do a good job of reconstructing, autoencoders have to be able to take their inputs and learn a representation of them that can compress them into only a few hidden units here, and then decompress them back out from that representation into a reconstruction. And it turns out that when we learn these compressed representations, they tend to correlate very well with the attributes of the data that we think are semantically relevant. Because in order to do this, the autoencoder has to sort of make decisions on what parts of the data are most important and what's worth keeping around and what's a minor detail that we can throw out. Now, we talked about autoencoders as doing two things. They're a neural network with a reconstruction loss, and there's a bottleneck layer in the middle that forces the network to compress its data. I mentioned before that autoencoders were not generative models. This is true in the sense that you can't really interpret them as learning a probability distribution in a strict sense, because you can't interpret them as doing compression in a strict sense. For instance, if your space of inputs is sufficiently small, in fact, they can just learn an identity function. But to the extent that they do compress their inputs, you can think of them as a sort of implicit generative model. Because there is a very interesting connection between compression and generative modeling. That connection is that the way you do compression is by defining a probability model on the things that you want to compress. And in your compressed code, you assign the shorter code words to the more likely data. And in fact, the better you can model something, the better you can compress it. And the better you can compress it, the better you can build a density model of it. Those two problems are basically sides of a coin. So based on this idea, there's a class of models called variational autoencoders. And variational autoencoders basically take this picture of an autoencoder that we've come up with, and they add some formalisms and add some extensions. They make everything probabilistic. They talk in terms, instead of a reconstruction loss, of outputting a certain restricted distribution at the end and maximizing likelihood. And in doing all of this, I won't go through the derivation, but they manage to build a model that looks very much like an autoencoder, but that has clear semantics as a generative model. And it ends up learning better representations than a standard autoencoder. And interestingly, you can sample from this the density function that it learns now. So you can use it in all the ways that you can use a typical generative model, even though it is, in terms of its architecture, very much like an autoencoder. So these are some samples of faces generated from a state-of-the-art convolutional variational autoencoder. You can see it does a pretty good job of realistically learning the space of what faces might look like. Each of these tiny pictures in the middle are actually interpolations between some of the bigger pictures. So it learns to separate out a lot of the factors that are relevant in determining the appearance of an image, which is significantly better than what the autoregressive models we were looking at earlier are able to do in terms of global structure. So this is variational autoencoders when they work really well. But in fact, the standard formulation as you implement it tends to suffer from a few problems. And this problem is that the encoder and the decoder tend to be limited. I mentioned that VAEs output, they add probabilistic semantics basically to the entire autoencoder picture. And in doing so, they define a sort of restricted class of possible probability functions, both in their encoder and their decoder. They model the output of the encoder as a diagonal covariance Gaussian, as it is, and they model the output of the decoder in the same way, conditioned on the output of the encoder. And the problem with these restricted families of distributions is that they're not able to capture all of the fine detail in images, and oftentimes you get generations that look really blurry like this. And the problem with blurry generations is that variational autoencoders have this interesting property that they do not encode what is not useful for them to decode, which means that if the decoder is not powerful enough to generate fine details like the texture of grass, then the encoder will never get the right gradients to learn to encode features like the texture of grass into its representation. And so they end up being hindered for representation learning in the same way. So the solution that people have come up with to this problem in VAEs is to take the autoregressive networks that we've looked at previously and actually to use them both in the encoder and the decoder. So now you have a series of very flexible density estimators, and you're using them first to encode something into a compressed representation and then to decode from that compressed representation. And when you do that, you end up with substantially more natural-looking images that have a very clear sense of global structure in them. Many of these images are identifiable as something. For the most part, it's natural scenes. This is a autoregressive variational autoencoder trained on the ImageNet data set, which is really challenging. We still haven't actually done a good job of being able to generate a lot of plausible objects from that. But it's definitely a step improvement over either the variational autoencoder or the pixel RNN model that we looked at alone. So I'm going to touch on a fourth class, roughly a fourth class of generative models really quickly. Until now, we've been concerned with this idea of learning a density function. And we've been sort of hamstrung by this idea because we've been tackling the problem of, well, how do you parameterize this density function in a nice way? And in order to do so, we've either had to factorize it in a sort of awkward way, or we've had to resort to the tricks of variational autoencoders, which use certain approximations and simplifications, which limits their capacity. So this class of generative models is called generative adversarial networks. And generative adversarial networks sort of sidestep the problem of having to explicitly define a density function altogether by implicitly defining one. Instead of defining a density function, which gives you the probability of any given point and from which you can sample, they just give you a network which is capable of generating samples from some implicit density function, but which never actually allows you to evaluate the function itself. The way this works is you have two networks. You have a generator network, which takes in random noise from some distribution which we'll fix beforehand up front. And it takes a sample of that noise, and it transforms it through a bunch of hidden layers into something that hopefully looks like an image, or a sentence, or audio waveform, or whatever you want. And then you have a second network called a discriminator. And your discriminator's job is, at random, it is fed either a sample from your actual data distribution or a sample from your generator network. And its job is to classify whether the sample is a real image or whether it is generated. And in doing so, your discriminator ends up learning what the rules of the real image data set are that distinguish them from the generated image set. And the way you train your generator is by maximizing the same cost that you're trying to minimize in your discriminator and just backpropagating the gradients all the way through from that loss through the discriminator and then backward through the image and through the generator. And so your generator learns to fool your discriminator, and simultaneously you train your discriminator not to be fooled by your generator. And these two networks, when you train them simultaneously, play a sort of minimax game. And hopefully, if you train it right, that converges on a scenario where your generator is unable to distinguish the real from the fake inputs, and your generator generates inputs which look convincingly like the real data. So these are bedrooms generated by a generative adversarial net. You can see this is basically state-of-the-art in terms of generating samples that are at once sharp and coherent and contain all of the characteristics of bedrooms that we're interested in representing. And the pictures that I showed you earlier of the birds and the ants and the volcanoes are also from this process. Because the only thing that the discriminator has to do is generate convincing-looking samples, this training procedure biases you toward learning a model which is really, really good at the task of generating convincing samples rather than necessarily at estimating likelihood or covering all parts of the distribution or things like that. So I'll try to conclude by saying that if I can impress upon you one idea through this presentation, it's that we have a lot of models for doing generative modeling and unsupervised learning in general. They all sort of have their drawbacks. We don't have a perfect model yet. This is very much an active area of research. But we're going to need to be able to do a good job at it. Because if you think about the world that we exist in, it's a world that has many orders of magnitude more unlabeled data than labeled. If we think about the way we learn to recognize cats versus dogs, actually, most of you probably did not sit down with the ImageNet data set and look at 1,000 labeled examples of cats before you learn to distinguish what a cat is. Because we do a good job of leveraging the unsupervised data that comes in through our visual system every second. And because we can leverage this data, we're able to learn the concept of a cat having seen only 1 or 2 examples of a cat. And if we want to build intelligent systems, we're going to have to figure out how to do this in a good way. And generative models are a promising path forward in that direction. So I will finish with what I think is just I personally think this is a pretty cool example of generative modeling. Somebody trained a variant of a variational autoencoder, basically, conditioned on a description, a one-sentence description of a certain scene, it learns to generate little thumbnail pictures of what that scene might look like. They trained this on a data set of common objects and common scenes that have captions provided for them. And then they evaluated this model by feeding it some scenes which are highly implausible in the real world. They fed it a stop sign is flying in blue skies, or a toilet seat sits open in a grass field. And lo and behold, the model is able to capture the meaning of these words and what they look like well enough that it does a kind of convincing job of generating what a toilet seat sitting in a grass field might look like, even though it's almost certainly never seen this before. And so it can generate these, it can hallucinate or imagine or create things which are almost certain never to have existed in the real world. And so if you want to be philosophical about it, you could say that this network is capable of generating dreams, which I think is interesting. Anyway, that's all. I'm here later if you have questions. Thanks, everyone.